So let's now have a look at a short animation to have a look at how the movement of H plus is actually taking place in this acid-base reaction. So initially we've got our HCl acid and our H2O, which in this case is functioning as a base. So the first thing that will happen is we're going to have the H plus coming away from HCl and being added onto the base. So let's have a look at that movement. So the H plus is moving away from the Cl minus and moving on to the H plus. So this is consistent with what we know to be the roles for the acid and the base. The acid is the proton donor and the base is the proton acceptor. So you can see that the acid is donating its H plus to the base and the base is accepting that H plus. So you can also see after the H plus has been removed from the HCl that all that's left of that component is the Cl minus, which we call the conjugate base, because in theory that Cl minus could actually accept an H plus in a different acid-base reaction. What about H plus plus H2O? What's that going to come together to make? Well, that's our other product. So now we have three hydrogens, but one of them is actually positively charged, so we have an extra plus there. So H plus added to H2O creates our other product, which is H3O plus, which is the conjugate acid. So hopefully you can see based on this that through the movement of H plus from the acid to the base, we're actually changing what we have for each compound. The HCl turns into Cl minus and the H2O turns into H3O plus. And once we've got the products, we've now got the reversal of the acid and base. So what was the acid to begin with has now turned into the base. Conjugate base is what we call that. And what was the base turns into the conjugate acid, which in this case is H3O plus. So just to try and solidify this a little further, let's look at this step by step. So we've got our acid, which is the H plus donor, and the H2O, which is the H plus acceptor. So the first part is where the acid will actually donate its H plus, as you can see from this blue dotted line, where we're getting the movement of that H plus away from the Cl minus and onto the base. So this is consistent with the characteristics of both the acid and the base. And as soon as that H plus leaves the Cl minus, we've now got one of our products, which is the conjugate base, because it now has one less H plus than when it started. And we also see that the H plus and H2O come together to form our conjugate acid. So the conjugate acid is basically a base that has accepted H plus. So it has one more H plus than when it began. Whereas the conjugate base is the acid that's lost one H plus. So it has one less H plus than when the reaction began. So you can see the end products in this last box here. So essentially, by doing the acid-base reaction, we've turned the two reactants that were in the first box here into the products. So these other two boxes were just showing the intermediate steps or movements of the H plus to facilitate this change. So now that we've been through that example in detail of how the acids and bases behave and how they're changing into the products, which are the conjugate acids and conjugate bases, let's go through a method for actually determining which reactant is the acid and which is the base, and how we can predict this based on an equation such as the one we see at the top here. So the first step is basically to work out which reactant matches to which product. So there's actually going to be two pairs. One reactant will match with one product, and then there'll be a second reactant matching with a second product. And there's only going to be a difference of H plus between these paired components. So for example, the pair that we saw in the first session, first part of this lecture was H2O matching with H3O plus. So the difference between these two components is one H plus. So that's one of our pairs. So this kind of automatically allows us to work out that our second pair is H2SO4 and HSO4 minus. But again, the difference between these is 1H plus. So notice that H2SO4 has 2 hydrogens here, and this one only has 1. And we've also got the negative charge there by losing that 1H plus. Alright, so that's basically the first step. So we're doing that for both reactants. So step 1 is to find the first pair, and then step 2 is just to repeat step 1 and find that second pair. So essentially you're just looking for the components that are very similar to each other. One will be on the reactant side and one on the product side. And then all you have to do is work out how the pairs actually are different from each other. So for example, this first one that we identified is H2O and H3O plus. So to go from H2O to H3O plus, we need to work out whether H plus has been lost or gained. So these are the two possibilities, because if H2O is acting like an acid, then it will have lost H plus, whereas if it's acting like a base, it will have gained that H plus. So going from H2O to H3O plus, you can see that there's an extra hydrogen here and also an extra positive charge compared to the H2O on the reactant side. That shows you that to go from H2O to H3O plus, that H2O has actually gained an H plus, which is a characteristic of a base. Now let's do the same for our other pair, H2SO4 and HSO4 minus. So this one has hydrogen 2 there, and we can see there's only the single hydrogen here and also a negative charge. So this adds up to the fact that H plus has actually been lost. So you'll always have the same pattern with one of the reactants losing H plus and one gaining H plus, which means H2SO4, which is actually sulfuric acid, is actually behaving like an acid. And what we actually have is the H plus being moved from H2SO4 onto the H2O, which allows us to form the products we see on the right hand side here. So let's go through that again with the help of the slides. So firstly, we need to match up the pairs. So the first pair that is being identified here is the fact that H2SO4 on the reactant side is similar to HSO4 minus on the product side. So that's our first pair. So once you've identified that first pair, you can then work out whether to go from the reaction to the product has resulted from gaining H plus or losing H plus. So because the H2SO4 has more H plus than the SO4 minus does, that tells us that we've actually lost one H plus in that process. So the other product is between, the other pair is between H2O and H3O plus. So the difference between those again is that one H plus. And then for step 3, essentially you're just working out what we did before, how the reactant turns into the product. Is that by losing or gaining H plus? So for the ones, you're just trying to work out whether to go from the reactant to the product side, has this happened by losing or gaining H plus? So in the case of H2SO4, it's actually losing an H plus to become HSO4 minus. So we can say that H2SO4 has more H plus than SO4 minus does. Therefore, the HSO4 is behaving like an acid. Remember, the acids are the proton donors. Now let's repeat the same step for our second pair. So how does H2O turn into H3O plus? We can see that H2O is actually gaining H plus to become our product here, which is H3O plus. So to facilitate this loss and gain, it basically means that the acidic H2SO4 is being added on to the basic H2O. So that explains how the change is occurring in our acid-base reaction here. So the product of the acid that we've identified here, so we've got that first pair, the acid turns into its product, and we call that product the conjugate base, because in theory that conjugate base is capable of accepting an H plus in a different acid-base reaction and therefore is capable of behaving like a base. And what started as the base turns into the conjugate acid due to gaining that extra H plus. So again, in theory, that means that the conjugate acid could function as an acid in a different acid-base reaction. Alright, so within every acid-base reaction, we have these two pairs that I've been referring to already. So we've got the reactant and the product that match, and the second reactant and product that match as well. So the technical name for these are the conjugate acid-base pairs, because the acid actually turns into a base and the base turns into the acid. So the first conjugate acid-base pair will actually be an acid and then the product of that acid, which is the conjugate base. Because remember, the acid loses the H plus and therefore becomes the conjugate base. The second pair is between the base and the conjugate acid. So the product the base becomes in the course of the reaction. So if you look back onto this slide, you can see that the conjugate acid-base pairs are the ones that we'd identified here, where the reactant turned into the product. So for example, here H2SO4 and SO4 minus is one conjugate acid-base pair, and the second is H2O and H3O plus. So the ones that you've identified as the pairs using that previous method are always the conjugate acid-base pairs. So that first pair is made up of H2SO4, which is the acid, and HSO4 minus, which is the conjugate base, and then the second pair is the base and its conjugate acid, which in this case is H2O and also H3O plus. So this is another thing that you'd be expected to be able to do when you're looking at an acid-base reaction. Not only identifying which are the acids and which are the bases in terms of the reactants, but also what this matches up to on the product side, and therefore identifying the conjugate acid-base pairs. So for every acid-base reaction, you have two of these conjugate acid-base pairs. And within each acid-base pair, the difference between the components is always H+. So for example, H2SO4 becomes HSO4 minus by losing H+. So the difference between those two is 1H+. Just like between H2O and H3O+, the difference between those is 1H+, but to go from the left-hand side to the right, this time it's actually a gain of H+ instead of a loss. Alright, so we've got a second reaction here as well. So this is one that we saw earlier, where we had the HCl reacting with water. So let's identify the conjugate acid-base pairs for this one. So as we did earlier, we saw that the HCl matches up to Cl minus, difference between them being 1H+, and so does the H2O and H3O plus there. Those are our two pairs. So we can say that the acid pair that pairs with the conjugate base, in this case, is HCl pairing with the conjugate base, which is Cl minus, and then the second pair is made up of the base, H2O, and the H3O plus conjugate base. So notice that the only difference between each of the components in the pair, again, is that 1H+. Alright, so we've got one more example of how to do this. So essentially, the first step is always to identify the pairs, which is pretty easy in this case because I've color-coded it. So the difference between OH minus and H2O is 1H+, as is the case with HF and F minus. So that would mean the first pair is F minus and HF, so that's one conjugate acid-base pair, and the second conjugate acid-base pair is OH minus and H2O. Alright, so over to you guys to have a go at using some of these rules that I've shown you, and also how to identify which ones are the conjugate acid-base pairs as well. So if you follow that method that I showed you earlier in terms of working out which ones are the pairs and also whether the pair has changed by losing or gaining an H plus from the left to the right, so how does the reactant become the product? Is it by gaining H plus or is it by losing H plus? That will allow you to work through these three questions. So please pause the video now and have a go at these three questions. Okay, so the only real way to answer the first two questions in terms of which components are behaving like an acid and which is behaving like a base is to go through that method I showed you earlier, where we work out which reactant is turning into which product, and from there you can work out whether the reactant is behaving like an acid or a base. So the first pair would be between OH minus and H2O. Again, the difference between these is 1H plus, and the second pair would be HNO3 and then NO3 minus. Again, the difference being 1H plus. So once we've identified those two pairs, now we need to work out how the reactants become the products. So let's start with our OH minus H2O. So which of these has more H plus? Would you expect OH minus to have more H plus or H2O? Well, because this one has two H's and this one only has one, that's a good indication that the product actually has more H plus. So we can say that going from left to right here is actually due to a gain of H plus. So which are the components that gain H plus? Is it the acids or the bases? Well, it's actually a characteristic of the base. So OH minus is acting as a base here, and that means it's accepting H plus from the other reactant. So that kind of helps us work out what's happening to the second pair here, but let's go through it anyway. The difference between HNO3 and NO3 minus, this one has the hydrogen, this one does not. So notice that there's a negative charge here, which is a hint that what's been lost is a H plus rather than a hydrogen. But don't worry too much about that. So the difference between these two is the fact that HNO3 has lost H plus. So what does that tell us about HNO3? Is it going to be behaving as an acid or a base? It's meaning it's going to be behaving as an acid, which we already knew because we'd worked out that OH minus was the base. So there's kind of a shortcut in these, because if you've worked out that one's behaving as a base, that means the other reactant has to be the acid. But it's always good to check just to make sure you've done it correctly. So let's work through these questions now. So which reactant behaves like an acid? So we can say that that's HNO3 is behaving like the acid, and why? So it is functioning to donate H plus. So to make this a complete answer, we should say what it's donating H plus to, and that's to the base, and the base compound in this case is OH minus. So that tells us the why we know it's HNO3. So which reactant behaves like a base? That must then be OH minus. And how do we know that? The why? Because it is accepting H plus from the acid. And in this case, the acid is HNO3. Okay, so what about the last question here? Which are the two conjugate acid-base pairs in the reaction? So it's really quite simple now because we've already found which reactant matches up with which product. So we've got two lots of these. So simply the pairs are the conjugate acid-base pairs. So one pair is that first pair that we identified, which is the OH minus and then H2O. And then the second pair is the second ones we identified, HNO3 and NO3 minus. So what is the difference between OH minus and H2O? The only difference between these is 1H plus. Same with the difference between HNO3 and NO3 minus, which is how we know they're the acid-base pairs. Alright, so hopefully that helped you to solidify all the different things I've been showing you, and it'll help you to interpret all the other acid-base reactions we see for the rest of the session as well.